see, you can see that the modulation was extremely high. Okay, right. And this image, by the way, is what's on the cover of the book. Okay, so then I was going to tell you some things about Spring 8, about SACLA, the free electron laser in Japan that's seeded by the same system that seeds Spring 8. Spring 8 is the 8 GeV highest energy synchrotron, hardest X-rays in the world. So this is SACLA. And so you have a homework assignment, and I hope we'll have enough time at the end to go over the homework assignment before you get into it. But pay attention to this figure. This is when they're just starting up. So the way they start the FELs is they have all of these magnet modules, each a few meters long, and they have, I don't know how many, 100 of them, 50 of them, something like that. And when they start in the beginning, so where the electron beam is just entering the first module, but they only have a few modules there. And it's just like synchrotron radiation coming out from the first few modulations. The length is insufficient at that point to get free electron lasing. And so the radiation that comes out is just the same as the synchrotron radiation we would see at Spring 8 or the ALS or something. And the radiation comes out in essential radiation 1 over gamma square root of n, or gamma star square root of n. And this light blue is the radiation that they were seeing when SACLA first turned on, okay? And so this is a relatively large, it's not so large, maybe 10 or a few tens of microradians. I think probably around 10 microradians. So when they start, they're seeing synchrotron radiation, and the angular emission that they see coming out, which they collect on a phosphor. So the X-rays hit the phosphor, and it has a certain imprint size there. And then out of the back of the phosphor comes light, a sort of a near replica of what came in from the X-rays on the front, and they image that with a camera, a visible light camera. So when they're just starting, they have this big circle. This is the central radiation cone, and the accelerated people, the FEL people in particular, call that spontaneous radiation. That's the SASE process, okay? So they don't have lasing yet. Then they start putting more and more of these magnet modules as they get to 100 kilometers, or they get to a lot of, not 100 kilometers, many meters, and maybe even 100 meters. Then different things start to happen. They see that as they put in more modules, the intensity doesn't go up linearly with the length of modules, but it starts going up exponentially. That's because there's a gain length. And eventually they get to some fraction of a kilometer and they reach saturation. Along the way, as they're seeing the intensity ramp up exponentially, this circle of radiation starts to get smaller and smaller, and eventually it's this little thing, which is like a microradian. And that's because the coherence has taken over, and the angle is no longer set by the 1 over gamma square root of n, but now the angle of emission has narrowed. So as this thing gains in amplitude and the modulation and all these n squared effects come in, it collapses. So one of your homework assignments is, if you were part of a team making the very first observation of FEL action, what would you expect to see? And one is, number one, you expect to see some exponential gain as you increase the length by inserting more modules. Second thing is, you expect to see the radiation cone collapse to something much smaller. Okay, so keep that in mind for tonight's or for tomorrow's homework assignment. So this is, this was a unique feature of the SACLA FEL for many years. It turns out that the LCLS at Stanford, its magnetic modules all operated at the exact same K. You couldn't change it. You could not open and close the gap at LCLS. I think the K was something like 3.5, but that was it. So the only way you could change the output energy was to change gamma, which they did. So they went from soft X-rays to hard X-rays, and they did a lot. But when SOCLA came on, it was using undulators of the kind that we use with synchrotrons, where each of the modules, this is representing 8 modules, insertion device 1 to insertion device 8. And so and each of these can have its K value, magnet strength set, and that will generate a certain wavelength for a certain electron beam. What's shown here is a game they played. Remember, they could get to saturation without you only using about half of the modules. So the second set of modules in this experiment have a different K. Okay, so all of the magnets here, magnet structures, are all set to some value K2, whereas over here, they were all set to K1, okay? So what does that allow you to do? It allows you to generate 2 different wavelengths, 2 different photon energies for pump probe experiments. So here's the electron beam comes in, the first half of the undulators, okay, and their K value and their K value. So they have a certain undulated period, but the K value is variable, so they can vary the wavelength. And what comes out, they call it the first color. What they mean is the first wavelength or the first photon energy. So some pulse comes out. So there's an electron bunch coming in. For every electron bunch coming in, this is going to happen. And there are many electron bunches coming one after the other. So this will happen repetitively. But anyway, so here's what the electron beam goes in. There's some K value set, and out comes the first color as they have determined with the undulator equation. Then there's a magnetic field, a 4-part magnetic field that deflects the electron beam around and back into the second set of undulators, whereas the radiation is still just going in a straight line. So in the end, this first radiation, it was running with the electron beam up to this point, but now the electrons are getting delayed and the X-rays are not. So the X-rays wind up coming out first, okay? As the electrons go into the second group of magnet structures set to a different K and therefore a different wavelength, it generates a second color, a second photon energy or a second wavelength, and they're one behind the other. So the first color gets through first, and the second one is delayed because the electrons that drove it are delayed. And this is the variability that they can produce, 0 to 40 femtoseconds, okay? And each of the pulses, again, for SOCLA is around 10 femtoseconds. Then the electrons get dumped and the 2 colors go on to your sample. The first one would be a pump to make something happen, and the second one would be a probe to see, okay, what happened? How did the atoms or molecules rearrange the electron structure or something like that, okay? And this is the tuning range that they could get. So for different values of the beam energy, the electron energy, this is showing what kind of tunability they could have as a function of K. So it's a good tunability. It's a pretty broad. Oh, they say nominally 7 femtosecond pulses, okay? Stand corrected. So for instance, this is what it might look like on a spectrometer. There would be 2 pulses that came out, one corresponding to the first pulse, the purple pulse, here with a certain K1 value, and they're 13.1 keV photons. And then coming behind them is the blue pulse, and that would be 9.7. So that's an example of what they can do, but by changing the K values, they can get a wide range of the 2 photon energies, and they can have a delay that depends on how they set up the chicane, okay? So now I'm going to show you how they use that for an experiment that was never been even approached before and hasn't been approached since then, and that is to make an atomic X-ray laser. So until now, atomic lasers have been in the EUV. not even the soft X-ray region, or marginally into soft X-rays. And then a few years ago at SLAC, people were able to knock out a lot of electrons from neon atoms and just knock out core electrons using LCLS. And then with a lot of core vacancies, when the electrons drop down, they threw off photons, and with enough of them, it lased. And there was a laser around 1 point something keV. But this next experiment, which was done at SACLA, right here, was they produced a copper K alpha atomic laser. So let me see if I can explain this to you. So the scheme is as we just discussed it. So you produce two different pulses and with two different photon energies, and they choose the first one to come to be a slightly higher photon energy of just about 9 keV. And this is going to hit a copper sample. So they're going to have actually a copper foil here. I forget how thick it is. It's not so thick, but they're actually going to burn a tunnel through it. So they're going to have this thin film of copper, and they're going to drill actually a tunnel. I forget what the aspect ratio is. Maybe it'll be on the next slide, but they actually drill through there, and they produce all of the atoms get hit by basically a 9 keV electron, which knocks out a K-shell electron. So all of in that cylinder, that tiny cylinder, every copper atom has lost one electron from the K-shell, okay? And then comes the second pulse, okay? And the second pulse could be one of these two energies. These would be what's called K alpha 1 or K alpha 2 if it comes from an atom. But what's happened is the first pulse has left all these copper atoms in an excited state. They've got a vacancy in the n=1 level, and for sure, if you wait, and you don't have to wait long, it's femtoseconds, and the atom will rearrange by dropping an electron from n=2 to n=1, and it'll throw off a photon. Okay, and that's the beginning of the lasing process. But suppose with all of these atoms sitting there, they've just lost their electron. So they're just into the excited state now, and they have not yet dropped down. And in comes a pulse at just the right energy, which is resonant between n=2 and n=1, and it takes that one of the electrons in the n=2 state, and it oscillates it between n=2 and n=1, and it eventually drops into the n=1 ground state and gives off a characteristic photon. And because of the splitting at the upper levels, you can get two different photon energies out of that. And this is work from a lot of people, but Makina Yabashi in particular. So for those of you who go to SACLA to use the FEL, look for Makina Yabashi and Hitoshi Tanaka, and please say hello. Okay, so here's what they saw then. This is the emissions that they saw. And remember, it's a SASE process, so there's some statistics in all of this. So this is showing how many photons, normalized, how many photons are coming out at what photon energy from this copper cylinder, the little tiny copper cylinder. And what's coming out is these extremely narrow lines, both for K alpha 1 and K alpha 2. Okay, and so this just repeats what I said before. The first pulse of photons, which is going to knock out an n=1 electron, it actually drills a small cylinder of copper atoms in the excited state, and it's 120 nanometers in diameter, because that was the focal spot of the photons, and it's 20 microns thick. That's the thickness of the thin copper film, okay? And each of the copper atoms just in the cylinder has an n=1 core hole, okay? And then the second seed pulse comes along, but it has random spikes because it's a SASE process, okay? And it's quite wide, 40 eV wide is the SASE process for them. And so it can drive either copper K alpha 1 or copper K alpha 2. It just depends on the noise. Which was there a noise spike to push the copper K alpha 1 or the copper K alpha 2? And the 1.7 EV line width comes because of a lifetime. Okay, it's a lifetime effect, and it's actually related here to the timing of the second pulse getting there. So you guys are not so into laser things, or at least not yet. How does that go down, or was there some comment?
I'm a little just confused about that very last point about the lifetime. Like, can you talk about that? Is that delta tau the timing between the two pulses?
I think it's not. I think it's actually that it doesn't say it here. I think it says it in the book. But there is a lifetime for that copper K alpha 1 to copper, for the N equals 2 to N equals 1 transition. The lifetime is extremely short because it's right next to a high Z nucleus. And so it's extremely short. And they had to keep this delay down to the absolute bare minimum, or else when the second pulse came through, all the transitions would have already happened. So the answer is, Lorena, I don't remember what the lifetime was, but the lifetime, if we can look in the book, because I remember pursuing this with some effort, what is that lifetime? And if you put it in here, you get this 1.7 EV, okay? Anybody else want to comment on anything? So it's a historic experiment. People have been trying to make lasers at ever shorter wavelengths and into the X-ray region for decades, and pushing. And so always with atomic lasers. And then the FELs came along and cut off the whole game. Yeah, the FELs are lasers also, but they don't produce as narrow a line. And there's something intellectual about doing it with an atom, not with a free electron laser. And so this is now regarded as one of the classic experiments in laser physics. Okay, Pohang light source in Korea, in Pohang, which is on the East Coast. And here's the FEL there, and the accelerator here. And there's something else. So this, I think I only have photographs to show. That photograph I showed of the first experiment at Sackler with the light blue ring, which with only a few magnet structures was the central radiation cone and then collapsing to the little thing. That was done by guys at Pohang. They worked with Makina Yabashi and Hitoshi Tanaka to do those experiments. And now there's a Swiss FEL, which is up and operating. It doesn't go to 10 kilovolts. I think it goes to something like 5 kilovolts, but it is also up and operating. And then the biggest of them all, which has now been operating, I guess, about 2 years, maybe more, is the European X-ray free electron laser, which they abbreviate EU-XFEL. And it is so long that it goes between 2 German states. So, and by the way, this is it's in a Hamburg suburb, and the community, the Hamburg city community, is so supportive of Daisy Lab and their free electron laser that when you take the metro system, the subway system, they have these, they always have these little posters advertising this, that, or the other thing. I frequently see posters about Daisy Lab or the free electron laser. At any rate, they have this enormous underground tunnel, and there are houses above here. And this is Electra. This is in Trieste, Italy. And it has the Fermi laser, and it's in the EUV, and it is the one that operates with the seed. So we had a question about that last time, and I think the next slide is going to get to us. And as you can see, they're right on the Adriatic Sea. This is Trieste below. This is Slovenia. Actually, if you get up on a hill here, you can see Slovenia and Croatia. So it's an interesting place to work and to visit. So, so now we're going to talk about seeding the free electron lasers. So the problem we have with SASE is that starting from noise, we get all of these different micro bunches within the main bunch, and they're separated, and their amplitudes vary statistically. It just depends on how many electrons happen to come together in a certain place to start the process. And within the bandwidth that's allowed, they have different frequencies. So there's all these, what did we say? Something like 300 spikes come out with SASE, which they reduce dramatically by a factor of 30 using what they call self-seeding, which we talked about last time. But what about if you could just seed? What if you had a laser that had enough intensity and electric field? The electric field is always the driver. It's what's in the Lorentz force. Intensity is not there. What if you had a laser that you could inject from the beginning to start the modulation process, not wait for some little spike to occur or a little group of electrons, hundreds or thousands of electrons come together and just have the right wave properties, okay? What if you could have a laser to do it? Well, the laser electric field has to be strong enough that within a short distance, it produces modulation stronger than the SASE would have, okay? And so currently, and probably for a while, you can't do that with hard X-rays. And in fact, even for EUV, like Fermi, you can't quite do it there either, but there is a trick you can play that people have known about, and that Fermi really, really played the card. They played a strong card, actually 3 strong cards, which I'm going to show you about. So this comment here is just that if you're going to have a seed, it has to have a strong enough intensity that its electric field dominates this modulation process early on. So here's the scheme of it. This is new. We've seen this diagram before, but now we're going to have a coherent seed pulse, which has an electric field strong enough to modulate the electron velocities here. And a trick is played to convert those electron velocity modulations into density modulations. So that's what's coming next. Should I stop for a question or comment?
Yeah, I had a quick one. So for this seed pulse, is it the same wavelength that we're going to get out at the end, or do you have some selectivity in what you seed with?
So great question. So in the diagram I'm showing here, the seed pulse wavelength and the output wavelength would be the same, okay? But in the case that I'm about to show you, they use the seed as short a wavelength as they can get, and then they play a different game to get multiplying even more or reducing by some factor. So the process that there'll be a seed. So here's an example from Fermi. They're going to do this twice, but let's just see how it starts here. There's an electron bunch shown in yellow coming into the FEL section, what's going to be the FEL, okay? And they also, on top of that, overlaid with that yellow electron bunch coming in, is a shorter seed pulse. It shows here as 240 nanometers. So 240 nanometers is the third harmonic done with crystals of a Ti-sapphire laser. So Ti-sapphire would be what you can get at a short wavelength with a short wavelength at a high intensity. And it typically, we say it's 800 nanometers, but it has a broad spectrum. So I think here it's 780. So there's a Ti-sapphire laser at 780. They go through 2 crystals to triple it, which is a technique which laser people do all the time. And out of that comes a coherent laser pulse at 240 nanometers, 1/3, and that's made to overlap with the electron beam. And we'll need to know later that the electron beam is considerably longer than the Ti sapphire harmonic. So the Ti sapphire for Electra is something like 180 femtoseconds, but the electron pulse is more like a picosecond or 1.2 picoseconds. So they overlap it at the beginning and they leave a lot of area unaffected, okay? Now they both go into this first section, a magnet section, which they call the modulator. And so as the electron beam is going in here, the laser beam is forcing the electrons to oscillate quite strongly, okay? And it produces a very high velocity modulation. So all of the electrons are within a certain phase are going through this high velocity modulation. So you could imagine this as just being a velocity plot would be a high amplitude sinusoidal motion imposed on all of the electrons as they go through. However, we don't want a velocity modulation for free electron lasing. We want a density modulation. So they run it through what they call a different magnetic scheme, which they call a dispersive section. And what happens is you come in with velocity modulation, and there's a magnetic field here, and the different electrons with different velocity go through a different path length, a little bit longer or a little bit shorter, before they come back to the axis. So the strong magnetic field here is converting the velocity modulation into a density modulation in this direction, okay? And now the density modulation goes into this, what they call the radiator. So the density modulation actually is extremely sharp. So if you were to Fourier analyze it, you would find that there's a lot of harmonics there of the original 240 nanometer, and they're shorter harmonics. So like third harmonic, fifth harmonic. So the electron the density modulation of the electrons here is extremely sharp. And if you did a Fourier analysis, you'd find there's lots of components in there, harmonic components, higher harmonics. So something like eighth harmonic or something like that. And by the way, you can have even harmonics in this case. So now they set these magnetic radiator sections. They set the K value along with the electron beam energy. They set the K value to match an electron oscillation of one of the harmonics, not the fundamental that came in at 240, but maybe the eighth harmonic. So that would bring it from 240. Actually, I think probably, let's say something like the sixth harmonic. Okay, so there's a density modulation here, very sharp, but within that, there would be a distribution at 60 nanometers, some component of it. And that's what's going to get amplified in this next section. So they're going to take 240 over some harmonic number 6, and that harmonic process is called high gain, high harmonic technique. So not to be confused with HG, which we'll talk about next time, but this is set by electron tuning techniques, playing with the K value of the magnetic field and enhancing the radiation from that, what might be a relatively weak harmonic, but it just gets larger and larger and larger. And I see, and they're showing that outcomes a 40 nanometer duration pulse, X-ray or EUV pulse, okay? So they started at 240, and they must have set the K value here to play on the sixth harmonic, and they get that, and then the electrons go to, it says a dump. But anyway, they've gotten themselves with, they started with a seed, Ti sapphire at almost 800, 780, did the tripling, and sent that whole thing through and used this electron modulation technique, HG, to get a shorter pulse. And they actually do this, actually rather than send it to the dump, they're going to send it to another section just like this. So can I stop here for a second? It's a complicated process. So I guess I want to go to the next section, which I think is going to show the second HGHE. Oh, please, yeah.
So you said that the K value can be varied in order to obtain a higher emission.
Yeah.
Well, when they're varying the K value, I guess do they have a live feed of what's going on, or do they run it once and then try to calibrate there?
Yeah, I got your question, but I misled you a little bit. When I said they can vary K, what I mean was depending on what output wavelength they want here, they'll choose some K value and they'll make all of these the exact same K value.
Okay.
Okay, and if they wanted to pick out a different harmonic of this modulation spike that came in, they just have to choose a different K value. So here, they're actually setting the K value for lasing at this wavelength. So there's a beam energy of something like 1.2 GeV, and then there's a magnet period, etc. So and the undulator equation. Okay.
Thank you.
Okay, so here's another slide then from Chair. So what we were looking at up to now was just this first part. The seed comes into the modulation sector where it's driving high amplitude velocity modulation, and then the dispersive section just has a magnetic field, and it just exchanges velocities for densities. It just spreads out all of those velocities. And then he went through the two radiator sections, and out came the 40 nanometers, okay? And then there's a delay line. The DL is a delay line. And what they want to do is they want to go into a section like this. That's what this is. It has more of the radiator modules. These are the ones that are going to produce the FEL action. But it's going to have a modulator, a second modulator, a second dispersive section, etc. But remember that the electron beam coming in was longer than the laser seed. So this is the Ti-sapphire frequency tripled pulse, and this is the electron beam. And now coming out of here, here you're getting the nice radiation, FEL action at 40 nanometers. But as you know, as you get to saturation, that screws up the electron beam, that nicely defined electron beam that the accelerator people work so hard to produce now has all kinds of modulations on it. And so they want to do this a second time, but it's not going to work if they start with a crappy electron beam. So they go to, they go through a delay line, and the delay line is enough that the X-rays, the 40 nanometers, will go faster. The electrons will be slowed up. So this pulse will now, when they recombine, will be overlapping the clean part of the electron beam. And I say clean because when this electron beam goes through the delay line, all the modulations get washed out. There's magnetic fields there again that spread out all the different frequencies and everything else, and it smooths out the electron density. So entering the second, I'm sorry, here was the delay line. Entering the next HG section, okay, they start with a nice clean electron beam. The 40 nanometers, you know, it started out, what did we say? It started out at 260. Now we're operating, now we have radiation at 40 nanometers, and it's overlapping a clean part of this green electron beam. So as we enter the second section, the lasing has a good starting point, okay? And this whole thing goes through here. And again, they do the same trick of putting using this radiation now, the 40 nanometer radiation, to produce a high velocity modulation. And then they run that velocity modulation through a dispersive section. DS is dispersive, and it converts velocity modulation to density modulation, and it's a very sharp density modulation. So it contains all kinds of harmonics, and they set a new value of K on these modules to get a different wavelength, harmonic again. So they started with a third harmonic of Ti sapphire. They divided here by 6, I think was what we saw in the last section, and they can divide by some other number here. And this is a paper, by the way. I did not post this, but what I did was I posted just before class started a paper, what do you call it, a commentary in Nature Photonics by a guy from the Japanese facility, Hara. He just has a nice diagram, which makes this a little bit clearer than I did. I don't know why I didn't think to put that diagram in the book, but I didn't, or into my slides. Maybe I should do that now. But at any rate, I did post something. It's quite brief. It's mainly the figure is the only thing. There's only a few sentences that go with it that help. But anyway, it explains that process. So this is what they get then. This is photons per pulse versus photon energy. And this is like a tuning curve where they're playing with both the beam energy, okay, and then with the K values. And you see that, for instance, it's saying here with using the first section HG, and the second HG. The first one choosing the third harmonic. Oh, I'm sorry. This is the third harmonic of Ti sapphire. Then they took 6 harmonic in this section, which we just went over, and then they took a third harmonic in the last HG section. So they wound up having a total of 36 times reduction in wavelength. So Josh, this goes back to your question. They started with one wavelength, but then they used other techniques to get a sequence of reductions in wavelengths. Okay. Oh, this is a summary of the various FELs that exist today. I think this is everything. And it has the beam energy, the electron beam energy, gamma for all of them. What is the peak current? So for instance, at LCLS, it was 3.4 thousand amps, kiloamps, okay? Okay, and this is and then what is the undulated period that they use, and how many periods are there from front to back? So you see that in some of these cases, there are thousands, 5,000 at Sakla, almost 4,000 at LCLS at Stanford, and at the new European XFEL, which says here 27, basically I think it was really 18. This is how many undulated periods there were, okay? And LU, I know I want 2 different numbers here. This is the length of the magnet structures. So there's gaps between them. It's not counted here, okay? So for instance, LCLS, it's a little over 100 meters of magnets, periodic magnet structures, broken up into small components, which you can figure out from some of the other numbers here. And the FEL in Europe, in Hamburg, is 175 meters. The actual length, I thought I put that in there, but I don't. Oh, here we go. The length. What is the actual length of this thing? So for LCLS, it's 2 kilometers. Only a little over 100 meters was magnet structures. The rest is space between them. That gets to 2 kilometers. But the European XFEL had 175 meters of magnet structures, but a total length of 3.4 kilometers. And the peak powers are all up in the gigawatts. So this also comes into one of the homework problems. The synchrotrons were the soft X-ray ones, like the ALS, were typically a watt of power. And the hard X-ray ones like APS or ESRF were more like 20 watts. But the FELs jump into the gigawatt range. And that's basically because of this n squared effect. The 10 to the 8th or 10 to the 9th electrons in the bunch, which are, let's say, maybe 10 to the 8th of them in some electron density wave, all of those electrons are radiating in phase. So the electric fields are adding before you square to get the intensity. So with this coherence brought on, this what I call the n squared effect, this nice modulation has gotten you an extra factor of the number of particles in that little electron wave. So it's of order 10 to the 8th, maybe a little bit more than that. So you went, for the hard X-rays, you went from about 10 or 20 watts to something like 10 to the 9th watts, gigawatts, okay? Actually more than that, okay? Because the number of electrons in the bunch, I said, was somewhere between 10 to the 8th and 10 to the 9th. Okay, and they have different polarizations. I see, so this slide is not the latest slide. Oh, I see, no, it is the latest slide. The mode of operation is showing, like for instance, for Fermi, it's seated. Actually, this statement shouldn't be here with Flash. It should, which is also at Hamburg. It should be over here. So that's Fermi. So that's the mode of operation. It's a seated. And the others were all sassy, but we've added the phrase self-seated because almost all of those, well, because all of those facilities are now self-seated. I don't have it for the EU XFEL, but that it may have happened and I just didn't make note of it. So I'll make those few small corrections there. How are we doing on time? So comparing undulator radiation and FEL, the differences, some of the differences are spatial and temporal coherence or just partial coherence, spatial filtering, uncorrelated emitters, you know, all the electrons are moving around in the undulator bunch without any orderliness, whereas for the FEL, they become correlated. I haven't talked to you about this one, but the FEL has what we call true phase coherence and mode control, and the undulators, the synchrotrons don't really have that. We just did filtering. We didn't do anything that would improve the phase or get all the electric fields lined up or anything like that. We just threw away a large number of the electrons, which were outside a small diameter. And within that small diameter, each of the electrons radiates completely independent, but they all produce the same, they're each producing the same interference pattern with the Young's double slit. So that's a difference, okay? Okay, I think that's enough of that. Oh, these are just some references. John Mady was a graduate student. He was working on this on his own, and he coined the phrase free electron laser. These Russian guys, Kondratyenko and Saldin, have had a lot of papers from the beginning, and Saldin is likely, if there's ever a Nobel Prize, Mady would have been one, but he died last year. Saldin is another, Claudio Pellegrini is the other. This is the paper that introduced that rho FEL parameter and showed that it was, you could use it to predict all the qualities if you wanted. And these are books. The two well-written FEL books, Schmuser, Dollhaus, Rosbach, and Chris Behrens have one. and the new book says X-rays. The old one just said ultraviolet. The new one says X-rays. And Chris was a postdoc at the University of Hamburg, and his job was to take the old book and add enough that it covered the X-rays. Okay, and Kwang-jae Kim and Zhirong Wang and Ryan Lindbergh, all at Argonne. Kim and Lindbergh at Argonne, and Wang and Lindbergh, by the way, is a Cal PhD graduate, and Kwang-jae used to teach in the physics department in Cal. Okay, and some other books. Okay, so I want to get rid of this, and I have something else. Do I still have you? Yeah. Much time? No, we have a half hour. Did anyone want to say something? I guess I cut off all the slides pretty quick. No. Okay. These are the homework problems for the FEL. And I guess you can see them. I don't know if you can read them, but you can see them, right? So the first one says, what controls the spatial coherence of an FEL and how is it achieved?
We're still only seeing your PowerPoint. Maybe you're only sharing the PowerPoint window?
Yeah, I got to stop sharing and then I have to reshare. Thank you. And now you should see it, right? So these are the four problems. None of them are particularly, anyway, here are four. So the first one is, what controls the spatial coherence of an FEL? So does someone want to comment on that? Short answer.
Doesn't it have to do with the microbunches?
Well, it has to do with the lateral size of the electron bunch. Remember, with the undulator radiation, we had to put a pinhole in front of it. And with a real laser, helium neon laser or laser pointers, the pinhole is actually inside the cavity. With the FEL, there's no pinhole, but the beam itself, the cross-sectional area is very small. So it's just, the answer is by beginning with a very small lateral beam that satisfies our relation, d dot theta equals lambda over 2 or lambda over 2 pi, okay? What are the three primary electron beam and undulator parameters that lead to lasing? So what's the difference? What do you have to do how do you evolve from an undulator at a synchrotron to an FEL? What are the three things that you need? Well, one was you needed the spatial coherence. And does someone want to venture what the other two are? Remember that the undulator had to be really long. Okay, in fact, that was the main thing. You had to have a really, really long undulator. You go from a few meters to a fraction of a kilometer. So you need a longer undulator, you need a smaller electron beam, so you'll get the spatial coherence. And it helps if you have a higher current, because that way you'll have more electrons in the bunch that are lasing. And it's that fields that they produce that start causing the microbunching. Okay. The next one, you are participating in the first hard X-ray FEL lasing experiments. Various undulator modules will be moved into place and the resulting radiation observed. What equation describes the expected wavelength? Well, that's our, maybe that's not a good question. What equation describes the expected wavelength? Well, when you start, it's just the undulator equation. What are two crucial, let me do something here. Rather than say what equation, whoops. There we go. Can you see that that's gone? Yeah. Okay. What are two crucial observations, both relatively simple, that can be made that will convince you that lasing has occurred? So this we talked about at the beginning or at some point in the lecture today.
Professor, would
Yeah.
this be like the SASI radiation versus the narrow lasing, basically?
Yes, I'm sorry. This is SASI. I should have said that this is SASI. Well, the first it says hard X-ray, so it has to be SASI. There's no seeds. So go ahead.
Go ahead, Neil, if you want.
Yeah, so I guess if we're talking about observations, it would be that you'd want to see that SASI radiation narrowed to like a lasing
Yes.
radiation if you're starting the FEL, right?
Yeah, so that's one thing you'll see. What's the other one that you'll see?
Exponential gain.
Exponential gain, great. Okay. The third question is, what is the bunching advantage of an FEL vis-a-vis an unmodulated electron beam as an undulator radiation? How many extra orders of magnitude can you get from that? So what is the advantage of the bunching?
The electric fields add within the bunch.
Perfect. Okay, so that's true. And then the last one, self-seeding is used with SASI FELs. Oh, self-seeding, not seeding with a laser. Self-seeding is used to narrow the radiated spectral bandwidth. Explain how this works. So you'll just have to go back and get the diagram that shows the diamond crystal being inserted halfway down the line so that it filters the incoming radiation spectrally by 1 part in 20,000. It's a big, it has a spectral bandwidth of 1 part in 20,000, whereas the beam coming in is 1 part in 300 or 500. So you just have to go back and find the diagram, and there's a diamond crystal there that it's basically a filter. It filters what radiation can get through to the next section, and in the next section you start all over again, but you don't start from SASI, from some statistical accumulation of electrons in what appears to be a wave. Rather, you start with what came through, powerful radiation, which is phase coherent, that got through that crystal. So, and also, it'll make a little bit more sense now. When the halfway down, you had this diamond crystal in transmission that filtered the radiation, truly filtered the radiation. And the electrons, if they went through the crystal, they would have destroyed it. So the electrons go through a chicane, those 4 magnets that deflect the electrons off to the side and then back in again. And in doing that, they smooth the electron bunching. So because just at the end of that long first section, just before the diamond crystal, you've got saturated lasing, SASI, but the electron beam is, because you're near saturation, the electron beam is completely modulated, okay? And it's not the right place to start the next lasing place. So the chicane, again, smooths that out. I don't know if that was part of the question, okay?
For 6.8, isn't the, like, how many orders of magnitude might the peak power, like, what's the improvement? Isn't that dependent on how many micro bunches you have?
Yes, basically yes. Remember that the electron bunch was so long that it could have a bunch of these little electron waves in there. And so each one of them has an n² effect just for itself, but for the other 300, they're not related to each other in phase, but they still add up. So if you had the power from one of those little bunches, you could roughly say, well, if I multiply that by 300, I'm going to get it that way. So you don't need 10 to the 9th electrons in each of those little bunches, in those micro bunches. There's not enough electrons for that. But you could say maybe 10 to the 8th, and the other 10 or 30 times that would get you the extra factor. Okay. So I think that's enough for today, unless we want some issues that we want to go over. So this one is due, I guess, in a week. Isn't that the way Defan works it? Yeah. Okay, so I think next time we'll start laser high harmonic generation. You take a Ti-sapphire laser and you focus it into an inert gas, and out comes a comb of harmonics. And the chemists use that for probing, and the pulses. So first of all, you can get to really high harmonics up around 50 or 100 eV. You can get even higher than that in photon energy, but usually with a lot less intensity. But at any rate, you focus this laser, Ti-sapphire typically, but not always anymore, and it's intense enough to take electrons right off the atoms that are in the gas. So each of the ideally, each of the gas atoms loses an electron, a valence electron. That electron is now free, and it's in this intense laser field, and the intense laser field accelerates it away from the parent atom, or actually ion, accelerates it away, and then the laser electric field turns around and it comes back again. And it goes far enough away that it's not necessarily going to recombine, actually. There's an efficiency of recombination. But at any rate, it gains a lot of energy in the laser field. And when it comes back, there's plenty of energy. And because it's repetitive, they come out in harmonics, a comb of harmonics. Yeah, and even harmonics only, unless, well, for the most part, that's the general way we explain it, but it is possible to get others. Anyway, that's what we'll talk about next time. The pulses are typically femtoseconds, but there are ways to make them get down into attoseconds, and so we should talk about how does this process work? What are the equations so we could really understand it? And what kind of intensities can you operate at? It turns out you typically operate at 3×10⁻⁻ watts per centimeter squared, for which if you figure out from that intensity, what is the electric field? And it's not quite as strong as the binding field of the electrons in the atom. It's a little bit less than that, but it's enough to pull electrons off. Okay, and we'll go through that. And why would you not make that intensity higher? That might even be better. You could get more acceleration and more energy of the electrons. But if you do, something goes wrong. And what goes wrong is you produce a plasma. Okay? So we'll go over a lot of these things starting next week. And we'll probably do that for 3 weeks. And I think for the plasma, for those people who are interested in the plasmas, I think we're going to have enough time to do 3 lectures on the plasmas also. So it may be that some of you have so little interest, you don't have to come for that. But for the plasma people who are concerned about it, we should communicate by emails, but we'll have time to do that. Okay, so have a good weekend. See you Tuesday.
Thank you.
Thanks.
Thanks. Bye.